In the last lecture, we introduced the idea of a quantum circuit. What we said is that a quantum circuit is a representation in which we show how the quantum logic flows from left to right, and it has components which are given by the gates or the operators which act on inputs or even on intermediate states. It has a very important component known as oracles, which is used to compute specific functions, which was, as we said, is like a black box computing, very similar to the way the subroutines are called for in classical computing programs. And we also have a meter-like thing which sort of tells you that you are actually making a measurement. Now, what you also pointed out is that the process of measurement does not give you the output corresponding to each of the inputs, which could be in a superposition of various states. The information is already there before we make a measurement. But when we make a measurement, out of the various possible outputs, only one output would be determined with certain probability, which depends upon what is the weight of each state in that. Today we will be talking about the applications of a very different applications, which will be quantum teleportation. But before I come to that, let me first talk about one theorem which I have been talking about but not having proved it, and this is known as the quantum no cloning theorem. The principle is very simple. The quantum no cloning theorem simply says it is not possible to find a unitary transformation which will duplicate a given state and write it onto a blank state. Well, basically what we are pointing out is that the xeroxing of a quantum state is not possible. Now, before you give the proof, let us look at what the process of duplication does, for example, in a Xerox machine. Now, in a Xerox machine, you start with two things. One is the original, which you want to be copied, and another is a blank page on which you want this copy to be made. So, corresponding to the blank page, I have what I will call as a standard state. If it's a single qubit state or whatever, I could take that as the state 0, and the original is the state psi which I want to be copied. So basically, a cloning would require that you take a blank state and a state psi, you find a unitary operation which gives me, in place of this blank state psi itself, and of course, as you know, in a Xeroxing, the original is returned back. Now, this is what cloning would mean. Now, we are claiming no unitary transformation of this type exists. Which does above. Now, let us see why not. Now, the proof is actually fairly trivial. So, basically we will say, supposing this were possible, we will prove it by what is known as reductio ad absurdum. So, supposing it were possible and there existed, if it were possible, and if there exists an U which did it, then U acting on 0 direct product with psi should give me psi psi. Now, since I cannot talk about one type of gate specifically for duplicating a specific state, if such a unitary transformation exists, in order that it is useful, I must have the same U duplicate a different state also. So, let us suppose it duplicates some state phi as well. So, I should get phi cross phi. The argument is very similar to my Xerox machine argument. You do not have a separate Xerox machine for copying different origins. So, if you have a Xerox machine, it will copy both. Now, if this is true, then notice what happens if I take the product of psi with phi. So, we have seen that this then is psi Now, I introduce a 0, 0. Notice that this scalar product is actually 1. So, I am multiplying it with 1, phi. But then this bra is psi 0 bra and this ket is 0 phi ket. So, therefore, this is can be written as compactly as psi 0, okay. And of course, there is phi 0, but let me come back to 0 phi or phi 0, it does not matter. Now, let me introduce here u dagger u. Remember u dagger u, u being a unitary matrix is identity, so I can always introduce this. So, u acts on 0 phi, u dagger acts on the bra psi 0. So, I must get this to be equal to psi, psi and phi phi. So, this is nothing but psi phi square. So, this is what I want. Now, this is possible only if the state psi and the state phi, they are identical, in which case both the sides become equal to 1, or if psi is orthogonal to the state phi, in which case the scalar product is 0 and 0 is equal to 0, because scalar product of psi phi equal to its square has the solution that it is either equal to 0 or equal to 1. So, therefore, psi and phi cannot be arbitrary states. If cloning is possible, if there is a machine which can clone a particular state psi, the same machine can at best clone a state which is orthogonal to it. And since we are looking for operators which would be cloning an arbitrary state, this tells me that our original assertion must be wrong and cloning is not possible. Now, this is used in what is called as a quantum teleportation. Refer to the slide. For those of you who have had at some time seen this old television serial called Star Trek, you must have been familiar with this phrase, beam me up Scotty, where the captain of the ship, Captain Kirk, used to ask his engineer to energize him at that point and then reassemble the energized captain in another place. And this is in principle teleportation, taking something from one place to another. Now, of course, we are not talking about teleportation in this science fiction language, but the principle is to send a quantum state from one point in space to another. Now, the way we would do this is, and this is a pair of names which you will get accustomed as we go along in this course. Instead of just saying that I have two people, one is called A, another is called B, in quantum computing it is traditional to give them names. So we have a person called Alice and another person called Bob, and Alice and Bob have become inseparable from the discussion of quantum computing, as we will see later. Now Alice has a state which is written as, so Alice has, let me state the requirement, Alice has a state alpha 0 plus beta 1, and this is the state which she wants to send to Bob, and Bob could be anywhere. So Bob is not at the same place, so that Alice cannot simply hand over. Now notice, either Alice does not know details about this state, that is, what are these alpha and beta, so that she cannot simply call up Bob and say that, look, this is alpha, this is beta, why don't you just make a state with this. Even if she knew the details, since alpha and beta are complex numbers, in order that Alice can give this precise information to Bob, the requirement would be, in principle, that infinite number of places will be required for describing a quantity alpha or beta, because it need not be a terminating expansion. So therefore this is not possible. Alice cannot make a measurement, because if she did, she would only get alpha or beta with some probability, and in the process also destroy that original state. But the question is, how does Alice then send that state to Bob? Now in order for them to do it, there is some things assumed, that Alice and Bob, who have known each other for some time, in the past they met, and they decided to share 1 qubit each of a Bell pair. Remember that we talked about Bell basis, and let us be specific and say Alice and Bob share 1 qubit each. For convenience, I will assume Alice shares the first qubit, Bob has the second qubit of a Bell state. And there are 4 Bell states. You can do teleportation with any one of them that you like. And this state that I take here for illustration purpose is 0, 0 plus 1, 1 by square root of 2. Now this is an entangled state. So it's not a state which you can write as a state with Alice multiplied with a state with Bob. This is an entangled state. Now, so with this notation, what I will do is assume that this is Alice's state. This I will call state 1. The first qubit of Alice I will call as the bit 2. So Alice has bit 1 and bit 2, and Bob has bit 3. Now let us look at how this process is carried out. I will try to explain each part of this circuit. This is a standard teleportation circuit. Let's look at that, and then I will tell you how exactly it is able to do the teleportation. So notice this first understand what is happening in this circuit. So there is this state psi which is equal to alpha 0 plus beta 1, which is with Alice. This and this are entangled Bell state, and out of which the first qubit is with Alice and the second qubit is with Bob. I will call this as the first, the second and the third. So what Alice does is to interact this psi with her part of the del state. Now having done that, Alice does certain operations. So this is what the red rectangle here is telling you what Alice does. So Alice will pass the first qubit through a Hadamard gate and then will make a measurement. And Alice will make a measurement of the second qubit as well, but in terms of time, the first Hadamard gate precedes this second measurement. So one Hadamard gate on the first qubit and a measurement of the first and the second qubits is what Alice does. Okay, so let us, before coming to the second part of this operation, let us try to understand what has happened. So we will write down, remember that what we had, we said that Alice has qubit number 1 and 2 and Bob has qubit number 3. So to start with, what I have is the following state. We have alpha by root 2, I am rewriting this, 0, let me write it down and then we will see how this has been written. This is a 1, wrongly written there. So look at what has happened. So my original state psi is alpha 0 plus beta 1, and this is the entangled state, 0 0 plus 1. Now I can rewrite them in a slightly different way. I can write this as 1 over square root of 2 alpha 0 0 0, explicitly separated out Alice and Bob, plus alpha 0 1 1 plus beta 1 0 0 plus beta 1 1 and 1. Okay. With this, now let us go back to the circuit, what is happening. Look at the slide again. So this is what we have got, and the first step is Alice applies a C0, taking the first qubit as the control and the second qubit as the target. You remember the definition of a C0. So in the C0 gate, so Alice says C0. So Alice's C0 does the following. I have got 1 over root 2. So I only concentrate on Alice's section. So since the control bit is 0, here nothing happens. So this state remains as it is. So does this state, because here also the control bit is 0. Here the control bit is 1. So this 0 will become 1. Here again the control bit is 1. So this 1 will become 0. So how will we write it? We will write this as alpha. Let us return back to our 3 qubit representation. This will be 0 0 0, the third qubit belongs to Bob, plus alpha 0 1 1 plus beta 1 1 0, because this is 1, so this 0 has become 1, plus beta 1 0 1. So this is what we have got. Look at the circuit again, the slide again. The next step is Alice applies a Hadamard gate to her first qubit. Now remember what the Hadamard gate does. A Hadamard gate converts a 0 to 0 plus 1 by root 2 and converts a 1 to 0 minus 1 by root 2. So if you look at this picture again, the state now becomes the following. So after Alice has Hadamard gate, the state we get is 1 over root 2 alpha. Hadamard gate is applied on the first qubit. So therefore, what I would get would be, it was a 0, so I will get 0 plus 1 by root 2, and the other two are unaffected, so they were 0, 0. The second one again is the same because the first qubit was 0, so alpha 0 plus 1 by square root of 2, and this was 1, 1 plus beta, so this was 1, so it will become 0 minus 1 by square root of 2, and this is 1, 0 plus beta, once again 0 minus 1 by square root of 2, and of course this is 0, 1. Now what we will do is, before proceeding further, because now two measurements are coming up. Two measurements are coming up because bit 1 and the bit 2 will have to be measured, because now the Hadamard gate has taken place. So let me rewrite this by combining terms in a particular way. So if you look at this, the slides again for a moment. So the thing is, look at it this. So I have here alpha 0, 0, 0. See, what I am going to do is this. I have, so far as Alice is concerned, I have 4 types of state. I have 0, 0, 0, 1, 1, 0 and 1, 1. So I will put this thing together, and there is another 0, 0 coming up here. So I will put this plus this. So I can rewrite these in the following way. So let me just illustrate it here. There is a 1 over root 2 and 1 over root 2, so there is 1 over 2. So I get 0, 0. This is for Alice. Now look at what is here. If it is 0, 0, I got alpha 0 plus beta 1. So I will write this as alpha 0 plus beta 1. And likewise, you can combine the other states, write it as 0, 1, a little bit of inspection is required. It is alpha 1 plus beta 0 plus 1, 0 with alpha 0 minus beta 1 plus 1, 1 with alpha 1 minus beta 0. Now, so if you look at the slide again, I have got 4 different types of measurement that Alice can make. So Alice actually makes a measurement here. Now when Alice makes a measurement, she gets either 0, 0, 0, 1, 1, 0 or 1, 1. Now depending on what she gets, she will now pick up a classical channel like a telephone and tell Bob that what did I get. So Bob would, I insist again that this is a classical information, exactly 2 bits of classical information that Alice is sending, which is easy. So therefore now let us look at what can we do. So come back here again. Supposing Alice tells Bob that I got 0, 0. Now notice Bob doesn't have to do anything. He already has alpha 0 plus beta 1, which is the state sign. Now suppose Alice told Bob I have got 0, 1. Now look at this is Bob's state. So Alice's measurement gives you 0, 1. So Bob's state with Bob is alpha 1 plus beta 0. On hearing from Alice that she has got 0, 1, Bob knows this is the state he has. So what he does is, at his end, he applies an X operator, which will convert it into alpha 0 plus beta 1, which is nothing but my state psi. Now suppose, I'll just illustrate once more. Suppose Alice got the last one, 1, 1. Then Bob has the following state. Bob has alpha 1 minus beta 0. Now this doesn't quite look the same state as we started with. So therefore what Bob does is to first change it, to apply an X gate, change it to alpha 0 minus beta 1. At that stage he applies a Z gate, which will make it alpha 0 plus beta 1. And you can work out what happens. The first case you don't do anything, Bob already has psi. I have given 2 more, and the last case you can work out yourself. So at the end of this process, what we have achieved is that Alice had started with a state alpha 0 plus beta 1. Alice and Bob both share a bell pair, and by doing certain measurements and operations by Alice, and then a classical communication channel, the Bob is able to get that state. That is the process of teleportation. There are 2 questions which arise in this situation. One is that we never said how far is Bob from Alice. In other words, they could be separated by space-like distances. So are we able to transmit a state with a speed greater than that of light? Because that would, if that were so, it would be against the principle of relativity. Remember I said one part which is essential in this operation is the classical channel. There is a classical information which Alice must inform Bob, and so therefore that must take place with following the special theory of relativity. And finally the situation is that have we been able to copy a thing? In other words, has cloning been done? Once again the answer is no. If you look at what Alice has at her end after these operations are done, you will find the original state she has become either 0 or 1, and Bob has simply recreated the state which Alice had from the bits that he had originally. He has now also lost his part of the qubit. So this is the process of teleportation.